Hi everyone, my name is Brandon, and I'm with the Space and Terrestrial Autonomous Robotic Systems Lab, or STARS Lab, at the University of Toronto Institute for Aerospace Studies. I'm here to tell you about my work on the localization of humans in GPS-denied environments, such as indoor settings. I will present my work on the addition of a motion classifier into the standard inertial navigation system. The role of the motion classifier is to adjust the parameters in the system such that they are optimal for the user's current motion type, which in turn improves localization accuracy. This work was presented at the 8th International Conference on Indoor Positioning and Indoor Navigation in Sapporo, Japan. Foot-mounted inertial navigation is a localization method in which an inertial measurement unit, or an IMU, is mounted onto a user's foot. Through dead reckoning, the IMU's linear acceleration and angular velocity measurements are integrated to provide a full 6 degree of freedom state estimate, including the position, velocity, and orientation of a user over time. A key application for this technology is first responder localization. For example, firefighters often must navigate within unknown dangerous environments, such as the one seen in this video. By knowing the location of these individuals, their safety and utility in emergency situations can be maximized. As GPS localization fails in indoor settings, we must rely on other localization techniques such as foot-mounted inertial navigation. For this application, however, we require a high-accuracy localization estimate that can be confidently relied on. Relying on a single IMU is challenging due to sensor drift, which results in unbounded error accumulation over time. To combat IMU drift, we take advantage of the human gait pattern in which the foot makes contact with the ground at regular intervals. During these points of contact, called mid-stance events, the velocity of the foot and the IMU is approximately zero. In this video, we see this to be true. Using a motion capture system, the velocity of a marker attached to the foot appears to be stationary at each mid-stance event. When this occurs, we can directly observe the velocity state of the system. This zero velocity measurement is typically injected into the state estimate through an extended Kalman filter. A zero velocity aided system can produce position estimates of a user with error under 1% of distance traveled. Our system architecture is shown here. The system relies on a zero velocity detector to observe when midstance occurs, and in turn passes zero velocity measurements to the filter. Typically, these detectors are a function of the most recent IMU readings. When the magnitude of the linear acceleration and the angular velocity falls below a specified threshold, midstance is assumed. My contribution to this system is the addition of a support vector machine classifier that provides contextual information of the user's motion to the zero velocity detector. By knowing the motion type, the classifier is able to update its parameters such that it optimally detects zero velocity events. The importance of this action is illustrated on the next slide. The current challenge with thresholding is that a fixed threshold may be optimal for a uniform motion, but there is no guarantee that the same threshold will work when the user changes their motion. This is shown by highlighting the difference in a standard zero velocity detector output between walking and running motions, which is depicted in this figure. If we take a closer look, we can see that the walking threshold is not applicable when running as it is too low. Applying a higher threshold will capture midstance when running, but if this threshold is applied for walking, the likelihood of false positive detections increases, which results in step length underestimation. Ideally, our threshold should be able to adapt to the user's motion type. That is, it should increase during rapid movements and decrease during slow movements. To do this, we require additional information as to what type of motion the user is currently undergoing. If we can predict the motion type of a user, we can selectively tune the threshold to be an appropriate value for that motion type. Here's a brief overview on how we achieved this. First, we defined two key motion types for our experiment, walking and running. We then determined the optimal zero velocity threshold for each motion type. We collected training data for our motion classifier, labeling data as either walking or running, and used this data to train a support vector machine classifier that accurately estimates the user's motion type. That is, whether the user is walking or running. In real time, we operate our motion classifier, whose output controls the threshold that our zero velocity detector uses. This figure shows how our motion classifier performs in the case of walking versus running. We note that it closely mimics the user's motion, but has a small lag which is attributed to the transition period in which the user is speeding up or slowing down. While we primarily focus on binary classification of walking versus running, we note that this can be extended to further motion types. We trained a 6-motion classifier, which achieved an average accuracy of over 90% across 6 different motion types. In future work, we would like to extend our adaptive thresholding concept to include these additional motion types. We evaluated our adaptive threshold system on 5 different individuals within the hallways at the University of Toronto. Here we show 5 ground truth points along the trajectory that we can compare our estimated trajectory with. Our test subjects were instructed to perform 3 different types of motion trials: walking along this trajectory, running, and a combined case where they alternated between walking and running in the same trial. This illustration focuses on the combined motion trial, where our adaptive threshold system should outperform a fixed threshold system. Starting with the fixed optimal walking threshold, we see that during the running intervals the position drifts due to the lack of mid-stance detection, which is a result of the threshold being too low. Using the optimal running threshold, we no longer see this drift, as mid-stance detection is more robust with the higher threshold. However, our endpoint error still diverges from ground truth. Finally, when using our adaptive threshold system, we see that we achieve a higher localization accuracy than we did with each of the fixed thresholds. Summarizing our results that span over 1 kilometer of motion data and 5 different users, we see that on average our adaptive threshold results in the lowest endpoint error. It matches the accuracy of the walking threshold when the user is solely walking, and matches the accuracy of the running threshold when the user is solely running. In the combined motion trials, we see a decrease in error by roughly 10%. Thanks for watching. If you would like to see more videos like this, please subscribe to the UTIUS STARS YouTube channel.